All right, 21.2, the last section in Chapter 21 and the last section before your Chapter 20 and 21 test coming up very shortly. So we are talking about electric fields and the force that electric fields generate, how we draw an electric field, how it's similar to a gravitational field. And in a gravitational field, you have two masses which are attracted to one another, and that attraction is greater depending on their distance apart. Same thing with an electric field. You have two test charges, and those test charges have a force between each other that varies depending on the distance apart. How do we apply electric fields to what you may know about electricity when we talk about voltage or capacitance? Well, here we go. Potential difference. You had potential energy, which you remember is the energy an object possessed if it were to fall, essentially, a distance. And electric potential difference is measured in voltage, a change in V. So voltage, you've probably heard the concept of voltage, but what exactly is it? Voltage is just the work done by a charge moving through an electric field. So to figure out voltage is equal to W divided by Q. V is volts, W is work, and Q is charge. So it's very similar to potential energy. Now remember, our unit for volts is volts, our unit for charge is coulombs. What's the unit for work? Joules. So similar to potential energy. Now, when you have two uniform fields come in close to one another by placing two large conducting plates near one another, you're going to create an electric field. When you create an electric field, you're going to create some potential energy or voltage. So when I put two plates next to one another, I have the opportunity to create voltage. And in that example, voltage is equal to the strength of the electric field, E, times the distance those plates are apart. And it's important to remember that the distance those plates are apart is in meters. So if we take our electric potential here, and we have two problems with voltage. And the first example, two charged parallel plates are 1.5 centimeters apart. The magnitude of E, the electric field, is 1,800 newtons per coulomb. What is the electric potential across the plates? Well, remember, electric potential is equal to voltage. So we are looking for voltage. Voltage is equal to E times D. Well, E is our electric field strength, which is 1,800, times D. And D is the distance the plates are apart. That's 1.5 centimeters, or 0.015 meters. You multiply those together, and using 2 sig figs, we end up getting 27 volts. Part B of the question, what work is required to move a proton from the negative plate to the positive plate? What work is required to move the proton from the negative plate to the positive plate? Well, remember, V is equal to W divided by Q. We know our voltage was 27. We're trying to solve for work. Now remember, Q is a charge, and a charge of a proton or electron is the same. Proton is positives, and that charge is 1.6 times 10 to the negative 19th. We're going to multiply those two numbers together, and the work done by that single proton is going to be equal to 4.3 times 10 to the negative 18th. Remember that our unit for work is in joules, and that is our answer. So you've heard about voltage. Voltage is kind of the potential difference, or the potential energy that a charge has, the amount of work that it requires to go through. When charge is shared, all systems come to equilibrium when the energy is at a minimum. Different sizes spheres matter because, think of it this way, the larger the sphere, the more spread out that voltage is. So think of it as a blanket. I have a 4 by 4 foot blanket, and I'm going to cover a ping pong ball. I'm going to be able to wrap that ping pong ball a lot of times in that blanket. Let's say, for example, now I want to wrap a beach ball. I'm not going to be able to wrap a beach ball as much in that blanket. And that's kind of how voltage works. If it's spread out, has a large surface area, it's going to be spread out more, so you're going to feel less voltage. A couple things here when we talk about conductors. Conductors, the net force on each charge is 0, so you have no voltage. So it's at equal potential, so voltage is 0. If a charged body is grounded by touching the earth, almost any amount of charge can flow to the earth until the voltage is 0. So what we do, and this happens in your house with wiring and other things, is the earth, since it's the largest sphere that we have, is capable of taking on large amounts of voltage since it's so large and so round. It spreads it out so well. So that is kind of called grounding, where the earth can absorb large amounts of voltage. So we ground things. We wire them directly to the earth. Gasoline trucks do this when they're depositing gasoline to prevent sparks. This happens to wiring in your house. All right, a couple things to summarize electric fields near conductors. Self-explanatory with the electric fields near conductors. Outside of a container, the electric field is not often 0. All right, and what can happen is that can create cause a pink glow or a spark or lightning. Lightning rods are pointed this way, so the electric field is outside of the container. It's outside of the container, so the E is at the strong end, so it can absorb the shock of lightning rather than going directly to a house. When we talk about lightning, the voltage of lightning is millions of volts. Now, one kind of misnomer, and we'll talk about this more in chapters 22 and 23, is voltage is not as harmful as the current at which it goes through your body. Now, millions of volts can kill you, but you can survive millions of volts depending on the current at which it goes through. Last little thing here, we have an equation, capacitor. What is a capacitor? A capacitor is a device that holds charge. So we've been talking about test charges, all sorts of charge. A capacitor is a device that holds charge. Usually it's designed to hold a specific amount of charge. And how do we figure out capacitance, or how much the capacitor can hold? Capacitance C is equal to Q divided by change in V. C is capacitance, Q is test charge, and V is voltage. The unit for capacitance is a farad. Now, when you figure out capacitance, it's going to be a very small number. So sometimes we will see micro 10 to the 6th or pico 10 to the 9th, or sorry, pico 10 to the 12th farads. Nano would be 10 to the negative 9th. So the unit for capacitance is a farad. Q is a test charge, coulombs, and voltage is, or volts is in voltage. There's a wide variety of capacitance. It's controlled by the surface area. And if we look at an equation dealing with capacitance, it's going to look like this. A sphere has an electric potential difference between it and the earth of 40 volts. When it has been charged to 2.4 microcoulombs, what is the capacitance of the system? Well, remember, capacitance is equal to Q divided by change in V. Our test charge was 2.4 microcoulombs, so 2.4 times 10 to the negative 6 divided by our our voltage of 40.0. When you divide those two out using sig figs, you get 6.0 times 10 to the 8th. We're dealing with capacitance, so our unit is farad. So a couple things you probably have experience working with, capacitors and capacitance with farads. Probably not as much as you've heard the term voltage. But we have 3 equations that kind of summarize chapter 21 when it comes to electric field strength and test charges. We will apply those. You'll have some questions tomorrow. And as I mentioned at the beginning, this ends the section and the chapter, so you can expect a test very shortly.